Hello, and welcome to this presentation on the binomial distribution. It is assumed you have seen previous presentations on probability, on Pascal's triangle, and on the binomial series, as those presentations underpin the work we're going to look at here. We are going to consider the binomial distribution and its relationship and application in terms of probability. The diagram on the left-hand side shows you a typical binomial distribution curve, where P represents the probability of an occurrence and Q represents the probability of non-occurrence. There are many experiments and sampling processes that occur within industry that conform either exactly or approximately to the following requirements. Number 1. The experiment consists of a sequence of n smaller experiments called trials or samples, where n is fixed in advance of the experiment. 2. Each trial or sample results in one of the same two possible outcomes, generally denoted by success P and failure Q, although sometimes those can be reversed. 3. The trials or samples are independent, so that the outcome of any one particular trial does not influence the outcome of any other trial. So for example, if we take a sample of 100 components from a production line, it is assumed that this will have no influence on the next sample taken from the line. 4. The probability of success P is constant from trial to trial, or sample to sample. So for example, this theory cannot be used where the probability of a second or third event is different to that of the first event. For example, selecting a winning horse from two races when there are a different number of horses running in each race. That would mean selecting the winner had a different probability in each of the races. So from the previous slides, we can see the binomial distribution of probability relates to two events only. The probability that an event will happen, sometimes denoted as P, and the probability that an event will not happen, sometimes denoted as Q. So for example, when a coin is tossed, if the probability of the coin landing with its head upwards is denoted as little p, and the probability of the coin landing with the tail upwards is noted as little q, then p plus q must equal to unity, or 1. The binomial distribution is, for example, used for finding the probability of, say, landing 4 heads in 9 tosses of a coin, or in an industrial setting for determining the defect rates from a sampling exercise. And we'll see examples of these later on. A binomial distribution can be defined as follows. If the probability that an event will happen is P, and the probability that an event will not happen is Q, then the probabilities that the event will happen 0 times, 1 times, twice, thrice, n times in n trials is found by the successive terms of the expansion of Q plus P to the power n, taking the terms from left to right. And this is shown in the binomial series below. So from our previous presentation, we've seen this binomial expansion before. We've got Q plus P to the power n. And that expands as Q to the power n for the first term plus second term n times Q to the power n minus 1 multiplied by P, plus for the third term n times in brackets n minus 1 times Q to the power of n take away 2 times by P to the 2 over factorial 2, plus for the fourth term n times n minus 1 times n minus 2 times Q to the power of n minus 3 times by P cubed upon factorial 3, and so it goes on. We'll be using this equation in the following worked examples on probability. Note that the notation 2 exclamation mark, 3 exclamation mark, 4 exclamation mark, etc. relate to factorial 2, factorial 3, factorial 4 respectively, and they're shown in the factorial tables for reference. There is usually a button on the scientific calculator that we can use to calculate the factorials should we need to, usually symbol n factorial or n exclamation mark. Example 1. We're asked to find the probabilities of having A, 2 girls, B, at least 1 girl, and C, at least 1 girl and 1 boy in a family of 4 children, assuming equal probability of a male and female birth. So from the question, the probability of a girl being born, P, is 0.5. The probability of a girl not being born, or if you like, a boy being born, Q, is equal to 0.5. The number of children in the family is given as n, which is 4. So from the above, the probabilities of no girl, 1 girl, 2 girls, 3 girls and 4 girls in the family of 4 are given by successive terms of the expansion q plus p all to the power of 4, taken from left to right in the equation below. So the p plus q to the power n expansion is shown here from the binomial series. So for a q plus p to the power of 4, n is 4 in this case expansion, we will get, looking at the first term, q to the n, so that's q to the 4, n is 4, and plus n times q to the n minus 1 times p, so n in this case is 4 children in the family, times q to the n take away 1, so that will be 4 take away 3, p to the power 1. Next term, plus n times n minus 1, q to the n minus 2, p to the 2 upon factorial 2. So in this case that will be 4 times 3, the n take away 1, q to the 2, p to the 2 over factorial 2, which is 2. Plus the next term, which is n times n minus 1 times n minus 2 times q to the power of n minus 3 times p to the 3 over factorial 3. So in this case that will be n, which is 4, n minus 1 is 3, n minus 2 is 2, times by q to the power of p cubed over factorial 3, which is 6. Next term, following the pattern, we will now get 4 times 3 times 2 times 1. We will get p to the 4 divided by factorial 4, which is 24. Simplifying the q plus p to the power of 4 on the last line here, we get q to the 4 plus 4 times q cubed times p plus 6 times q squared p squared plus 4 times q times p cubed plus p to the power of 4. This is now our probability series based on the binomial theorem. Okay, example 1 continued here. I've just repeated the expansion from the previous page for convenience. So we're going to work out our probabilities for each of the terms here. So taking the first term in the series, the probability of no girls, all boys if you like, that's q to the power of 4. Q in this case is 0.5 raised to the power of 4, so the probability of no girls in a family of 4 is 0.0625. Taking the second term in our series, that's the probability of 1 girl in the family of 4, that's 4 times q cubed times by p, that's 4 times q, which is 0.5 cubed, times by p, which is also 0.5. That gives a probability of 0.25. Taking the third term in the series, that's for 2 girls in the family, 2 girls and 2 boys, that's 6 times q squared p squared. So that's 6 times 0.5 squared times 0.5 squared. That gives us a value of 0.375. That's the probability. Taking the fourth term in the series, this is 3 girls in the family. Probability is given as 4 times q times p to the power of 3. So that's 4 times 0.5 times 0.5 cubed, which is 0.25. And the final term in our series is for 4 girls, no boys in the family. That's p to the power of 4, 0.5 to the power of 4, 0.0625. Notice the symmetry there, that's because the q and the p in this particular case are the same value. Adding up the total probability, we should get a value of 1, which we do. If you add all these values together, you will get 1. So now answering the questions given on the previous slide, part A, we've got to find the probability of 2 girls from the above listing. Well, for 2 girls we can see that's going to be this probability of 0.375. So 0.375 is the probability, or 37.5%. Part B, the probability of having at least 1 girl is the sum of the probabilities of having 1 girl, 2 girls, 3 girls and 4 girls. So from our table, that's summing these probabilities here. There are 4 of them. So the 0.25 plus a 0.375 plus a 0.25 plus a 0.0625. When you add them up, you get 0.9375 or 93.8% approximately. An alternative approach for calculating part B is to take the total probability, value of 1, and from it subtract the probability of having all boys, the q to the 4 term in this case. So 1 take away the q to the 4 term, the all boys term, leaves you with again 0.9375. So the probability of at least 1 girl is 0.375, but an alternative way to approach that calculation. Example 1 continued. I've shown the expansion here and the various probabilities from the previous slide for convenience. So part C, we've got to find a probability of having at least 1 girl and 1 boy. Now that's the sum of these terms here. Okay, the 3 terms in the middle effectively, because the first term is having no girls, so that can't have 1 girl there, and the final term is having 4 girls, so there's no boys in there. So we cannot use those 2 terms because we want at least 1 girl and 1 boy. So summing the 3 probabilities together gives us a value of 0.875 or 87.5%. There's an 87.5% they will have at least 1 girl and 1 boy in this family of 4. An alternative way of calculating part C is to take the total probability, 1, and from it subtract the probability of having no girls, that's the q to the 4 term, and no boys, that's the p to the 4. So from our table above, if we add the 0.0625 for the q to the 4 term to the 0.0625, which is the p to the 4 term, subtract that from 1, we get the same probability as shown above. An alternative way of calculating the same value. I will leave you with exercise 1 to attempt. It's based on example 1 on the previous slide, and the answers are given in the bracket. Example 2. A dice is rolled 9 times. We're asked to find the probabilities of throwing the number 3, A, twice, B, less than 4 times, C, more than twice. So from the question, probability of throwing number 3, we'll call that P in this case, is 1 upon 6. There are 6 sides to a dice and one side would have the number 3. So the probability of not throwing a 3, call that Q, is 5 upon 6, where P plus Q equals to 1. The number of times the dice is thrown in this case, call that N, and that's 9. So from the above, the probability of no 3 being thrown, 3 being thrown once, twice, 3 times up to N times, are given by the successive terms in the expansion Q plus P to the power of N, where N is 9. So we've got our P plus Q to the N binomial expansion shown here again. So looking at P plus Q to the power of 9 expanded, the first term in the binomial series here is Q to the N, that would be Q to the 9 in this case, plus second term is N times Q to the N minus 1 times P, that's plus N, which is 9, times Q to the N minus 1, that's Q to the 8, times by the P. Next term, third term here, will be 9 times by 8 times by Q to the 7 times by P to the 2, all divided by factorial 2, which is 2. Our next term here is 9 times by 8 times by 7 times by Q to the 6 times by P to the 3 divided by factorial 3, which is 6. I've just expanded the first 4 terms here because that's all I need to help me solve this problem. Tidying up the expansion like q plus p to the power 9, I get q to the 9 plus 9 times q to the 8 times by p plus 36 q to the 7 times p squared plus 84 q to the 6 p cubed, etc. Example 2 continued here. I've repeated the expansion of q plus p to the power 9 for convenience. We're going to work out now each of the 4 terms in the series we require to answer this question. So taking the first term is q to the 9. That's the probability of having no 3 thrown in the 9th rows. So q to the 9 is 5 divided by 6, the value of q raised to the power 9, gives me a probability of 0.1938. Our second term in the series, this is the probability of throwing a 3 just once in the 9 times. That's 9 times q to the 8 times p. So that's 9 times 5 divided by 6 to the power 8 times by 1 upon 6, the probability of p here. It gives me 0.3489 probability. The third term in the series is the probability of throwing a 3 twice. So at 36 times q to the 7 times p squared. So 36 times 5 divided by 6 to the power 7 times 1 divided by 6 squared gives me a probability of 0.2791. And the final term I need in the series is the probability of throwing a 3 thrice, or 3 times. That's 84 times q to the 6 times p cubed. So that's 84 times 5 divided by 6 to the power 6 times 1 divided by 6 to the power 3. It gives me a probability of 0.1302. Now to answer the questions, part A required the probability of throwing a 3 twice. We simply look down our listing, that will be this row here, so the probability was 0.2791 or approximately 28%. Part B, the probability of throwing a 3 less than 4 times. Now that's the sum of the probabilities of throwing a 3 not at all, throwing it once, throwing it twice, throwing it 3 times. So in this case we simply add up those probabilities. Probability of throwing a 3 not at all is 0.1938, of throwing a 3 once 0.3489, throwing it twice 0.2791, throwing it 3 times 0.1308. When we summate those probabilities together we get 95.2%. Finally, part 3 of the question, the probability of throwing a 3 more than 2 times. So in this case we can work this out by taking the total probability of 1 and taking from that the sum of the probabilities of throwing a 3 0 times, once and twice. So think that through to yourself. We're trying to find the probability of throwing a 3 more than 2 times. So we use the total probability of 1 and from that we take away the probability of throwing a 3 not at all, throwing it once and then throwing it twice. So 1 take away the summation of those probabilities will give me 0.1782 or 17.82%. So the 17.82% probability of throwing a 3 more than 2 times. I'll leave you with exercise 2 to attempt on your own. It's based on example 2 on the previous slide and the answer is shown in the bracket. Industrial inspection of manufactured items. When inspecting items or components in industry, P is usually considered the probability the item is defective and Q is the probability the item is satisfactory. So in this case the binomial distribution is defined as the probabilities that 0, 1, 2, 3, 4 up to n items are defective in a sample of n items drawn at random from a large batch are found from the successive terms of the expansion q plus p to the power n. taken from left to right. The following example shows how that definition is applied in practice. Example 3. A machine is producing a large number of screws automatically. In a box of these screws, 95% are within the allowable tolerance with respect to the diameter. The remainder of the screws are outside of the diameter tolerance allowed. 7 screws are drawn at random from the box. We're asked to determine the probabilities that A, 2, and B, more than 2 of the 7 screws are outside of the diameter tolerance allowed. So P is the probability of a screw outside of the allowable tolerance, so it's defective, and Q is the probability of a screw being within the required tolerance, so that's satisfactory. From the question, the probability of drawing a defective screw, P, is 5%, or 0.05. The probability of drawing a satisfactory screw, Q, will be 95%, because P plus Q must equal to 1, or 0.95. The sample number in this case, N, is 7. So the probabilities of 0, 1, 2, N defective screws being drawn are the successive term in the expansion Q plus P to the power N, and again it's given in the box here below. Example 3 continued here. I just repeated the P plus Q to the N generic binomial expansion, convenience. Don't forget in this case we're expanding Q plus P to the power 7 screws in our sample, so that will be Q to the 7 plus 7 times Q to the 6P plus 7 times 6 times Q to the 5 times P squared upon 2, etc. Simplifying that, we get Q plus P to the power 7, that's Q to the 7 plus 7 times Q to the 6 times P plus 21 Q to the 5 P squared plus 35 Q to the 4 P cubed. I've actually given myself 4 terms there, but in this particular question I really only need 3 of those terms. So considering the first term in the series, that's the probability of no defective screws drawn from a sample, that's Q to the 7. Q in this case is 0.95 to the power 7 gives 0.6983 probability. Looking at the second term in the series, that's having 1 defective screw in our sample, that's 7 times Q to the 6 times P, so 7 times 0.095 to the power 6 times by the P, which is 0.05, gives a probability of 0.2573. And then the third term in the series having 2 defective screws, that's 21 Q to the 5 P squared, so that's 21 times 0.05 to the power 5 times by 0.05 squared. That gives a probability of 0.0406. There's another term, but I don't actually need this in the calculation. So part A, we've got to find the probability of having 2 defective screws in our sample. So again, looking at our listing here above, 2 defective screws is here. So the probability is 0.0406, or rounded up to 4.1%. So part B, we're asked to find the probability of more than 2 of the 7 screws being outside the tolerance. So I'm going to use the total probability, 1 here, and from that I'm going to take the probability of having no defect, the first term, 1 defect and 2 defects, so the first, second and third term of the series. I'm going to take the probabilities from 1. So in this case the calculation is 1 takeaway from the above table, 0.6983 plus the 0.2573 plus the 0.0406. Adding them up and taking them from 1, we get a probability of 0.0038 or 0.38%. So from the calculation, there is only a 0.38% chance that more than 2 screws out of the 7 screws will be outside of the tolerance. I'll leave you with exercise 3. It's based on example 3, and again the answers are shown in the brackets. Example 4. A foundry production run contains 500 similar castings. An inspection shows that 3 in every 20 castings are to be scrapped due to blowhole damage. If 30 castings are sampled at random from the production run, determine the probabilities that the sample A has 3 scrapped castings, B has less than 2 scrap castings. From the question, the probability of a casting being damaged, P is equal to 3 in 20, which is a value of 0.15. So note that 3 divided by 20 is 0.15. Thus the probability of the casting not being damaged, Q, is 1 take away P, so 1 take away 0.15 gives me 0.85. The sample size, N, is 30. So the probability of there being none, 1, 2, etc. damaged castings is given by the successive terms in the expansion Q plus P to the power of 30, taken from left to right. From our binomial series in equation 1 on a previous slide, Q plus P to the power of 30 can be expanded as Q to the power of 30 plus the N30 times Q to the power of N take away 1, 29, times by P, plus the N times by N take away 1, so 30 times by 29, Q to the power of N take away 2, so that's Q to the 28, times by P squared divided by factorial 2, and then plus the N30 times the N minus 1, 29, times the N minus 2, 28, Q to the power of N take away 3, P to the 3 over factorial 3, which is 6, and so on. So the expansion Q plus P to the 30 simplifies to Q to the 30 plus 30 times Q to the 29 times P plus 435 Q to the 28 times P squared plus 4060 Q to the 27 P cubed. Example 4 continued. I just repeated the expansion of Q plus P to the power 30 from the previous slide for convenience. So the probability of having no defects in our sample is the first term in our expansion, Q to the 30. So Q to the 30 is 0.85 to the power 30, and that's 0.00763 probability. Probability of having one defective casting, one scrap casting in our sample, is the second term in the series, and that's 30 times Q to the 29 times P. So that's 30 times 0.85 to the 29, the Q term, times 0.15, the P term. That gives us a probability of 0.0404. The probability of having two defective casts in our sample, that's the third term in the series, is 435 times Q to the 28 times P squared. So that's 435 times 0.85 to the power 28 times 0.15 squared, gives a value of 0.1034 as a probability. And finally, the probability of having three defective castings in our sample, that's the fourth term in our series, so that's 4060 times Q to the 27 times P cubed. So 4060 times 0.85 to the 27 times 0.15 cubed is a probability of 0.1703. So to answer the questions, for A, we've got to find the probability of 3 scrap castings in our sample, so that will be this term in our series, for the 3 scrap castings, the fourth term in the series, and that's 0.1703, or approximately 17%. Part B of our question is to find the probability that less than 2 scrap castings will be in our sample. That's given by the sum of the probabilities of no scrap castings in the sample and 1 scrap casting in the sample. So from our table, that will be this term added to this term. So 0.00763 plus 0.0404 gives us a total of 0.04803 as a probability, or rounding that up to 4.8%. I'll leave you with exercise 4 to attempt. that's based on example 4, and the answers are shown in the brackets. Finally, we'll look briefly at the histogram of probabilities. A pictorial representation of the terms in a binomial distribution can be shown using a histogram, and example 5 illustrates this. Example 5. If there is a 45% probability of a student successfully completing a part-time undergraduate course in 4 years, draw a histogram showing the probabilities of 0, 1, 2, etc. 10 students successfully completing such a course. So in this case, P is the probability of a student successfully completing a 4-year part-time course, and Q is the probability of not completing the course in the 4 years. So P from the question is 45%, or 0.45, and Q is 1 take away the 0.45, that's 0.55. The number of students here is 10. So the probabilities of 0, 1, 2, 10 students successfully completing the course is given by the successive terms in the binomial expansion Q plus P to the power 10, taken from left to right. So from the generic equation we had on a previous slide, equation 1, Q plus P to the power 10 is expanded as shown here. I will let you look at this expansion. You need to go back to equation 1 if you want to see the generic equation, but this is the expansion of all the terms in the series. Don't forget, if the n is 10, then the number of terms in the series is 11. The histogram of probabilities are continued here, just repeated these lines here for convenience here. If you put the values of Q equals 0.55 and P is equal to 0.45 into the above equation, you will end up with the successive terms shown here. I'll let you work them out for yourself. These can then be shown on a histogram depicting the probabilities as shown in the diagram on the right. So on the horizontal axis we've got number of students up to 10, and on the vertical axis probability of successfully completing the course. Here are the solutions to the exercise on the previous slides for your reference. Solution to exercise 1. Solution to exercise 1 continued. Solution to exercise 1 continued again. Solution to exercise 2. Solution to exercise 2 continued. Solution to exercise 3. Solution to exercise 3 continued. Solution to exercise 4. Solution to exercise 4 continued. I'll leave you with some tutorial questions to attempt. The answers are shown in the brackets. More tutorial questions. Here is the bibliography used to help develop the presentation. Some excellent reference books here I would encourage you to review for further information. I hope this has been of help to you. Thank you for viewing.